Okay, hey folks, our last topic in this module 3 is going to be on tunneling. And as you can see, I've got 3 learning goals dedicated to this topic. So let's go for it. First one, be familiar with the concept of tunneling and know how to solve the Schrödinger equations for this system. So let's find the slide all the way down here at the end. Okay, so by definition, tunneling is known as energy leakage by penetration through a classically forbidden region. So let's highlight that, through a classically forbidden region. So this picture here on the left is the standing wave approximation. And what we can see here is on this leftmost region, which I will label region 1, it effectively looks like our particle in the box problem, right? Where we've got a particle somewhere in here and it's free to move to the left and to the right. Now, the difference with this problem versus particle in a box, our potential barrier is finite, okay? So we don't have this infinitely large barrier. And because our particle, in this case, possesses the requisite kinetic energy, it can tunnel through this barrier, through what we'll call region 2, and make it out the other side, which we'll call region 3, at diminished probability. Okay. So this picture, the standing wave picture, is really just kind of showing a particle moving from left all the way to the right. In reality, we've got some more complicated stuff going on. So for example, in region 1, we would have an incident wave and also a reflected wave off the barrier. So some of the particles might bounce right back off. Inside the barrier, we've got this thing that's analogous to classical dampening. So the kinetic energy of the particle is decreasing as it moves through the barrier. And in addition, we can also allow for the fact that there might be some reflection off of the rightmost part of this barrier. And then eventually we get a transmitted wave at reduced intensity or reduced probability. So what we want to do now is solve the Schrödinger equation for all 3 of these regions using the appropriate boundary conditions. So for the first region, we've already done this, right? So in region 1, we're going to say potential energy equals 0. And here we have our Schrödinger equation. So we know how to do this. So let's go through that all the same. So I can rearrange my Schrödinger's equation to allow me to set up the ansatz solution. So we can say the second derivative in psi is equal to negative 2me over h bar squared, all times psi of x. We rearrange that into the reduced form, right? Second derivative psi of x plus 2me over h bar squared, all times psi of x equals 0. And recall, we make our standard guess where we're going to say psi of x equals e ax. And yes, we'll keep with that letter a for now. And then we know, of course, the first derivative of that is a e ax. And the second derivative is a squared e ax. All right, so plugging all of that in and eliminating the exponential, right? I'm making a shortcut because we've solved this before. We end up with a squared plus 2me over h bar squared, all equals 0. And thus a will equal the square root, so negative, right, 2me over h bar squared square root, okay? And so recall, we called all of that our wave number solution. So what we get for A is plus or minus I k, where k is all of that stuff inside the square root. Okay. And so then recall our general solution for the Schrödinger equation went something like this. A, some arbitrary constant yet to be determined, ikx plus b, e negative ikx. And of course, we could also write that as some linear combination of sines and cosines. And recall from our discussion with this solution, our A term here are particles moving from left to right, and our B term here is particles moving from right to left. So we can think of this AEIKX as the wave function describing left moving particles, and this BE negative IKX would describe our transmitted wave, or excuse me, our reflected wave. So the wave that reflects off of the boundary, right? That looks something like that, okay? So beautiful. We have our region 1 solution. Let's move on to region 2. So, oops, wrong way on my slides. So this region will be subtly different because now we have potential energy, okay? So we have potential energy right here. And we can see in this case, we're going to regard our potential energy as constant, and we're going to say that it is greater than the total energy as indicated on the graph. Okay. So let's do it. We can solve this thing. So following the same method we did before, I will write the second derivative in psi, and just collecting all of the constants and doing some algebra. I get negative 2m times the quantity E minus V, all divided by h bar squared times psi of x. Okay. So I first subtracted this V over, collected like terms, and then pushed all those constants through. So now rearranging that to the reduced form, right? We have second derivative in psi plus 2m times the quantity E minus V all over h bar squared equals 0. We're going to make our same standard guesses we did before, so let's write all of those down. Psi of x equals E ax. First derivative in psi is a E ax, and the second derivative in psi is a squared EAX. So same thing we did before. And now, as we might guess here, we're going to follow the same procedures. We substitute in our guesses, and then we can eliminate the EAX because that will appear in each term. Oops, and I believe I forgot to write a times psi of x there. Let's squeeze that little guy in. So times psi of x, and that all equals 0. Okay, apologies there. So plugging all of that in, we're going to end up with a squared plus 2m times the quantity E minus V all over h bar squared equals 0. And now continuing along here, I'm going to write that as a squared equals negative 2m times E minus V all over h bar squared. And at first this appears like we're going to get imaginary solutions, right? The square root of a negative. But if we see here that we imposed V must be greater than E, then we already know this quantity E minus V is negative. So now I'm going to rewrite that as positive 2m V minus E all over h bar squared. And now we can see that's going to give us a real solution. So then in other words, A equals the square root of 2m V minus E all over h bar squared. And I'm going to call this solution plus or minus kappa. So as we might notice, this is going to give us a wave number, right? But now instead of having just energy there, we have potential minus the energy. So I'm going to give that a Greek letter kappa, and now our solution will be will have real roots. So that's going to go as the following: some arbitrary constant c e to the kappa x without the I, right? Plus dE to the negative kappa x. And so now this becomes our solution in region 2, which, as you can see, is describing this exponential. We have an exponential decay, right, describing the transmitted particle. But we also would have something analogous to exponential growth, which would, I know looks kind of goofy and backwards here, but that would describe the reflected wave within the barrier. Okay, the last solution we need is the solution for region 3, and I'm just going to cut straight to it because we can see here it's the same setup that we had for region 1, albeit at a reduced intensity. So I'm just going to go for it. We know that that's going to be an imaginary solution because it's going to be nearly identical to region 1. And now I'm going to call that a prime E I K X plus B prime E negative I K X, where my K still means the same thing, square root of 2ME over H bar squared. But now what we can see here is these constants, A prime and B prime, those are going to be different than the constants from our region 1 solution. And as we might guess, my A prime term is still describing left moving particles, and my B prime term is still describing, A prime term is describing particles moving left to right, and my B prime term is describing particles moving from right to left. Okay, so that is a good place to stop. We're going to pick right back up with this in the next video.